is the INCREACE project about? It's a project on recycled plastics in electronics products and products with added value. And now you may wonder, why are we tackling this? Isn't this solved yet? Yes, you can use recycled content in electronics products. However, we have very special challenges within our project. So we look into 5 different business cases, which deal with, for example, food contact, with flame retardancy, with chemical resistancy, with electrostatic discharge, or with medical and skin contact. And those challenges that we face have specific different challenges. So it's on the one hand, on technical feasibility of using recyclates for these specific applications, but also, for example, on dealing with traces of contamination, with regulatory aspects that are not yet solved. And this is why we are looking in the project not only on the specific business cases and their direct implementation, but we really look into the entire value chain of the plastics recycling industry and the application, and look on it from very different angles. So of course, we also look into circular product design and the user involvement in order to close loops and really make recycling not only possible, but happening. We look into the regulatory and policy landscape. We look into new ways of sorting the plastic streams or the material streams. We look into environmental and cost assessments, or like we assess them in order to understand what the environmental and economic costs are and how to lever them. And we also look more on the macroscopic level, like on the understanding how waste can be understood as a resources and how we have to transition towards the circular economy on a bigger picture. And today we want to talk about maybe the core on the high quality recycling, because in this project we also look into different ways of different recycling technologies and their advantages in order to achieve these high quality recyclates, and also in order to increase the recycling rates in total. And therefore, we also look into combination of the advantages of these technologies. But that's something that you will hear now from the actual experts in the field. And I guess with this, I can already hand over to Martin.
Exactly. Alva is traveling today, so she is with us somehow in the train, but connection may fail. This is why I will take over here. If you don't mind, I would share my set of slides since we had some last minute changes.
Yes.
Just switch over and
yeah,
do it later. So I hope you can see right now.
We're not yet seeing the presentation mode, but yes, we see them.
Don't. Right now.
Now we see a paper.
Very funny.
Now it's still in the overview mode.
Check in this one. Give me about a second here.
Yeah, now it's good.
Now it looks better. Great.
Yeah.
Thank you. Switch over to that one. Yeah, the agenda, we will talk about an overview on the WEEE collection, recycling, and so on, to share our idea where we are today and what is research in this project is advancing to current state. We look into the mechanical recycling approaches that we have chosen. We look into the so-called solvent-based or dissolution-based recycling approaches. We look into chemical recycling. And finally, after a very short wrap-up, we look into best combination. There's a typo, sorry for that. Combination of recycling technologies, all the three of them exemplified with one fraction from WEEE. Ending with an outlook, and I hope we finish in time, that you have enough space and time for questions. WEEE collection, if you look into the overall share of small home appliances and large home appliances, cooling, freezing stuff from the Association Applier provided in 22-23, you see a high share of plastics coming from small domestic appliances and with a smaller share coming from large home appliances and cooling. If you look into the fate after WEEE collection and look where processing takes place, we also see that the amount really goes down from 100% collected to somewhat 58% somehow managed, and only, let's say, a minor part of it going into recycled material. Much is, even after being processed and collected, ends up in incineration or co-processing, which is not, let's say, considered to be helpful for circular economies. But still, we have a large part of losses coming from lack of documentation or collection. If we look into the kind of recycling technologies we have in place so far, we mainly talk about the so-called mechanical recycling, which is, let's say, the mechanical treatment of the e-waste, starting from size reduction, washing, cleaning, separation, sorting, and that stuff. And in the end, it is normally a re-extrusion, reblending, melt filtration, that stuff ending up in mechanically recycled plastics. In addition to that, we also have the so-called dissolution or solvent-based recycling or purification. Here we implement a solvent to separate, or to help to separate the plastic, the target plastic, from its contaminants, but we do not change the chain length. So it is not an attack to the polymer chain. It is really just a cleaning on a macromolecular level. This is completely different from chemical recovery, where we go into depolymerization or thermolyzers, pyrolyzers, for example, to break down materials into hydrocarbons, syngases, or monomers, which need to be repolymerized before getting polymer again. And this, of course, can be then re-enter value chains as a chemical recycled material or mechanical recycled material. Just for everybody to be clear what we mean with these terms. State-of-the-art WEEE recycling starts with a collection, whatever it is, then sent to specific companies. They do a depollution of manually, that they really take out specific materials nobody wants to have in final products. Then the material enters a shredder, magnet, and eddy current, separation of aluminium. We do have sorters who pick out printed circuit boards and other metals. And finally, we end up with a, let's say, organic or plastic waste fraction, which is sometimes in the same company, sometimes in a second company, used to be further separated. And one of the most common approaches here is to have a density separation, to split that material into a heavy plastic and a lower density plastic. And here it may happen that this is still undergoing a further density step at 1.0 to get an ABS, a PP, and a PS out of this one, which is the normal today's mechanical recycling route. The other stuff in the heavy plastic density fraction is normally sent out to incineration. So there's up to date, not really a huge valorization of that part. So we can conclude a large part of collected sorted WEEE plastic goes still to incineration. And on the other hand, why is that the case? It is because of many hazardous substances really concentrate in this heavy fraction. This makes it very difficult to recycle that one, and makes it easy to manage the hazardous compounds just by destruction and incineration. So this is probably kind of a reason why this is the current state of the art. If we want to increase the amount of recycled WEEE plastics, we face the following challenges. We have contamination in the plastics coming from impurities such as metals or other chemicals in the use phase, or other contaminants coming from legacy additives in the initial production. Without separating these contaminants, we have a problem in getting recyclates which comply with today's legal regulatory world. We have a material diversity. In WEEE plastics, we have more than 16 different polymers in use, and for sure we have to sort them to very high levels of purity to make use of them in downstream recycling processes. And this is not as easy, so we can do this with chemical recycling or the solvents. In mechanical recycling, we really we are stuck to, let's say, the state of the art of advanced sorting technologies, but this is, however, one of the largest challenges we face. In the end, once we really manage to recycle the plastics, it has to comply with the strict environmental and safety regulations. And if this is all done, there might be additional regulations or specifications in the industry who's considered to take over that material, which is a completely other set of data which you also have to supply in order to bring material back into the circular value chain. Finally, this is the reason why the current recycling rates for WEEE plastics are quite low, and many materials are lost for second or third life at the moment. So let's look how INCREACE and this group try to advance that state of the art. To see how it looks like at the moment. We have many different feedstocks here from different manufacturers, multitude of different polymers, qualities, whatever. This in the end even looks quite clean. I have seen even pictures from much dirtier products than this one. But you see that this is the challenge to make this something acceptable for industry in a second life. The next point is normally that the products are shredded, that the non-plastics are separated, and then we try to have these plastics sorted, as I said, by density. One of the basic clues is to make this density cut at 1.1 roughly, since everything which is lighter than that is only a smaller group of plastics like the PE, PP, and the unframe retarded PS and ABSs. And all the rest is ending up in the higher fraction. This can be handled somehow by another density cut at 1.0, for example, or downstream NIR sorting to make more defined fraction out of it. And you see here, there's another size reduction in there. And in the end, you produce a regranulated material by re-extrusion and recompounding, meaning you add additives to make that material more suitable for industries in that second stage. Okay. Complexity. Oh, sorry. These slides have been considered to be presented also by Myrek. I really stepped that over. So if you want to take over or add something here, please feel invited to do so.
Yeah, so I'll take over. I mean, you went over the basic process with, it's not all that complicated in the sense of like the number of steps. If you could play the video that's on the right-hand side, make sure the sound is off. But what you see here is one of our sorting steps at one of our machines. What we do here is over the belt, we have the pieces of plastic, but also any other like PCBs or any metal containing fractions. And this machine is one of our machines that separates out metal containing fractions and then the plastics. This still contains everything from polyethylene to ABS-PC and everything in between. So after this, we then go to the density step at 1.1, which then results in the fractions you see in the bottom. So going from our floating fraction, which has P, PP, PS, and ABS, the compounder then processes it further, separating it usually at the 1.0 density step to get the polyolefins and the polystyrenics separate, and sometimes further steps with near-infrared sorting. And once they have completed their separation, you get a smaller step as it is processed by them. And then at the compounder as well, they indeed, as Martin explained, make the new recyclate that can be used by the producers of products. So if you could go to the next slide. Then, of course, we already had some main challenges, but then specifically looking at mechanical recycling. And then mechanical recycling here is both the pre-processing as we do at Mirex, so that's up to the point of the bigger flakes. And then also the problems of mechanical recycling after us that really go from the big flakes to something that the producer can use. Martin already mentioned it, but the complexity of products, both in the number and type of plastic used, but also all the other materials and typically how they are connected. Like if you have 2K injection molding, there's no way we're getting that separate. But also if things are glued, which means that if plastic or metals are glued together, it also becomes a lot harder to separate and properly sort them. And this is something that can be addressed by considering the end-of-life status of a product at the design, which is something that has been discussed a couple of crash courses ago when we went over, okay, what is proper design of a product for the eventual end of life of such a product. Then, of course, there's also the problem that a lot of products contain different polymers. So something I will go into more is we try to cluster products that have similar polymer types to see if we can then increase the concentration of our desired polymers and make it easier for ourselves to separate out those polymers without contaminating them. And then for us, specifically high density plastics, that's why we have the cutoff point at 1.1 grams per cubic centimeter. It's because they're typically very hard, as Martin already said, with regards to hazardous materials that are being used. So often that's brominated flame retardants. And then we're also currently by legislation required to make sure those are incinerated at such a temperature that those flame retardants are destroyed. So one of the avenues there is to go towards solvent-based recycling, which we will talk about more. And then lastly, one of the items that is difficult for us, which is very popular with producers, is black plastics. They are perfectly fine in density separation, but if you want to do near sorting, then the machine does not see them because they don't reflect any of the light. And so there we're looking at new sorting techniques in the form of mere, or what we're now already doing to an extent with density sorting to get around the black plastics. Could you go to the next slide?
Sure.
So as part of the project, we did a clustering approach. So we have two clusters that we went for two main polymers. The first is polypropylene. And there we looked at different groups. We looked at toys, large household, small household / kitchen appliances, washing machine, dryers, and dishwashers. And we collected and sorted them and processed them separately to see what is the quality of the plastics you get. And then with the help of KU Leuven, they did the analysis. And then it was found that the small household appliances, but also toys and kitchen appliances have polypropylene fractions that are suitable to further go the mechanical recycling route, so to recompound them and to make new products out. Whereas, for example, with large household appliances, whilst they contain a lot of nice white polypropylene, which would be ideal for further mechanical recycling, they have the problem of glass fiber additives, which then does limit its further use due to the additives that are already in there and potential problems with machinery further down the line. If you can play the video on the right-hand side, that is the end step is how at MIREC, so that's the pre-processing mechanical recycler, we end with the floating fraction. So this is after we've processed a batch of only toys, hence the very nicely colorful mixture of plastics. But that also would mean for this batch that if you further process it, from what the KU Leuven found in terms of characteristics, it's a nice group, but it obviously comes with a color problem because it's all kinds of colors that you then mix to something that is in the middle of all of them. Next to the PP fraction, we also did the ABS PC fraction. So if you could go to the next slide. So in addition to the polypropylene fraction, which is already a fraction that is mechanically recycled, we also looked at PC ABS, specifically from copiers, modems, e-meters, and LCD TVs. So all four of them were again processed separately over all the lines to end at a fraction that contained PC ABS. For fractions such as the copiers, but also the e-meters that are predominantly white plastics, we could use near separation to sort out only PC and ABS without losing a massive fraction in terms of black plastics. And these plastics were then either sent to solvent-based recycling or they also went to mechanical recycling and compounding. And here we saw that the majority of the copier, modems, and e-meter plastics that we got out of our process were directly suitable for solvent-based recycling, which is also the next part of this crash course.
Okay, great. Probably to take over from here, you see that one of the benefits of solvent-based recycling is that we do not need a 95 or whatever, 99 plus purity in the feedstock. We can make use of materials which have that purity of only 70% of the target polymer, which makes it easier to be implemented in existing lines without having a, let's say, severe additional effort from additional sorting instruments. Yeah, solvent-based recycling. Okay. Let me start with this concept overview here in the beginning. The basic idea is that you take that material that we've seen up front, either if it's a colorful one or it's the whitish one or the black one, doesn't matter at all. We put it into a tank, we put in some solvents, which is specific for the target polymers. We stir it, sometimes we apply some heat, and in the end we have a dissolved target polymer, and all the other materials in that feedstock are either undissolved or co-dissolved. And in the downstream cleaning process, we separate first the undissolved matter by sieves and others. And in the second step, we can even separate co-dissolved material. Co-dissolved material can be additives like flame retardants and others, which are simply extractively eliminated from the polymer solution. And in the end, after cleaning, we precipitate the material, we dry it. In this process, all the solvent is recovered and reused in the process. And in the end, as the final product step is an extrusion, a degassing extrusion, we end up with a granulated product, which can directly be reused, or if you want to go back into some recompounding to adjust the product's properties. The basic idea is this is suitable for all thermoplastics. You can make this with very specific and also very safe solvents, and you can really highly purify impurities and contaminants. And in the end, you have, if you are lucky with your process, a competitive material with virgin feedstock. If the idea started for sure, as many others, in the lab 20 years ago. And in the meantime, we scaled that up first to a TL4 to our small technical lines. And we also have scaled this one to TL6 and even larger ones for other flame retardant styrenics, even until TL8 so far. So you see it is not only a stupid idea of some researchers, it has been put into stainless steel and larger scale applications already. So what did we find out in the INCREACE project? So we looked for sure again in the lab scale in many different fractions we got from mechanical pre-treatment. And we see here plastic fractions from emitters, copiers, and modems. And we looked with specific solvents into the shares of PC, ABS, and others. And you see that it is that the shares of PC plus PC ABS is quite high in all these fractions. And if we then go into the pure dissolution process, we achieved getting back a pure recycled PC, and as a co-product we also got a PC ABS. Same is true here for the copiers. Here we also produced an ABS and a recycled PC ABS, and in the case of the modems we only looked into the ABSs. You see it is here. Looks like a quite simple one for sure. The purification steps are not pictured, so it is a bit more complicated than just one stirrer. But let's look into into the results, and you see here that we end up with melt flow rates which are slightly higher than virgin, depending on what you take out for virgin for sure. We have average molecular weight distributions very similar to virgin, so there's no indication for a specific degradation somehow, despite the fact that we start from a very, very mixed feedstock. So it has been totally undefined from the waste that we got. So it is in the end quite funny that in the products are still in the same range. And if we look into the DSC, we also have the typical values here, which indicate that our products are really the indicated ABSs and PCs and so on. With respect to purification, let's look into some typical elements in that feedstock, which is on the one hand the bromine, which comes from brominated flame retardants. We have phosphorus coming from phosphor-based flame retardants. We have silica and calcium coming from typical inorganic fillers. And you see here that in the feedstocks, it is sometimes a bit higher brominated, no phosphorus in, but we still have higher filler contents. This is somewhere in between, and you see the monomer fraction is quite the purest in a way. In these two cases, we have some values of chlorine measured coming from any feedstock in that range, not directly identifiable. In the end, you see that the products we got out are really far lower than the feedstock, and this refers to both to the flame retardants on the one hand and also to the fillers, meaning if we apply the fine filtration as we did, we can get out these fillers from the material, from the feedstock. You see that the reduction rates are quite significant for all the reported ones. For the modems here, this is just indicating it is possible. You see a factor of 10 more or less. We know from other publications and also other studies that a stepwise further reduction can even go to a 99% reduction. But these are the typical contaminants. In INCREACE, we also looked for some others, and you probably have seen that bisphenol A is one of the most prominent candidates of, let's say, substance of concern in this kind of materials. And here we see how we manage to get down any BPA levels below any level of concern here in the range of 150 or 170. We're just asking for being below 1000. And I know from polycarbonate producers that this is still in line with what they expect. Looking into the overall mass balance of this dissolution-based recycling here, exemplified for the E-meter fraction, you see that the overall output is quite reasonable. You have something like 75% coming out as either PC recyclate or PC ABS. There's some others going out for sample analyzers. There's the coarse and fine residues. And as always, if you work in lower with lower capacities, you face the loss issue, which may be sometimes just water, sometimes it is losses to any kind of surfaces. So very typical one here. Finally, let's look into material properties. And let me please point out, this is not the one which is considered to be sent out to industry. This is before compounding, very important, since we did not only reduce the levels of flame retardants, so we may, of course, also have an effect on any other additives in there. So in the end, it is for us not surprising that the MFRs are probably a bit higher than usual. The average molecular weight distribution is still fine for us, and the TG are also still where we expect them. If you look for the PC here into other levels on the mechanical properties, you see, for example, strain break and whatever. These levels are lower than expected, but this is not critical to my knowledge, since this is easy repairable, let's put it that way, by recompounding in the end, since we took out some additives which have been applied earlier, so this is something which is not really a problem in to get it back into the value chain. Here the same is true for the ABS. Same story before compounding. Here, very typical result is that the impact Charpy is far below what we normally measure for nicely virgin compounded ABS. But again, this is easy adjustable by adding new impact modifiers to get back to normal values here. So that's for solvent-based recycling, and let's switch over to chemical recycling. Will help me here with presentation. Let me double check.
Timo seems to just have dropped out, but he's coming back. I think maybe his connection was bad, but I just saw him coming back.
Is coming back? So if
Yeah,
not,
I lost the
okay,
connection,
great,
but
thanks.
Now I'm back. I'm with my mobile phone now
Feel free to
connection
take
because I
over.
lost. Yeah. So yeah, I can start from this. So the target here is the chemical recycling of this WEEE plastics, and I start with the challenge. The challenge is that there are many different polymer types, and of course you can pyrolyze different types, but then if you target to the steam record, like here in our model, we see it in the next page. But if still continue about this, there are certain plastics which fit better to that pyrolysis approach, and certain which not. So ABS is not very suitable. You get, of course, acrylonitrile styrene there and some secondary products from those. If you pyrolyze those polystyrene, you get a lot of styrene, which is also not good for the upgrading, and you should not have it when you feed to the steam cracker. Polycarbonate, you get lot of oxygen, you get a lot of aromatics, also not good for the steam cracker. But then from polypropylene and polyethylene, you get this only hydrocarbons. Of course, there are impurities, but predominantly you get into the oil product, you get then hydrocarbon free of those kind of bigger contamination amounts. But impurities, what we have is halogens, bromine, chlorine, bromine from the flame retardants, as was said, and usually there's also some PVC or some other chlorine containing impurities. And then silicon, especially organic silicon, is of course the worst. If it's inorganic, like from talc or from glass fiber, it's not a big issue because then it's remaining in the jar, not going to the oil product. And then of course heavy metals are difficult, especially if we want to use this jar for something else than only incineration. The next slide is showing our approach. So from the left, we take some sorted fraction, which is not good enough for mechanical recycling at least. And then in this study, we have done this liquefaction, and the target is then from the liquefaction to take the fraction which is then suitable for steam cracker, but between the liquefaction and steam cracker, there need to be also some purification step, meaning upgrading. And then for steam cracker, you can get olefins, what you can use for in the synthesis of then new polymers like polyolefins or any other polymers also. Next.
Has he lost his connection again?
Okay, but I don't know why I was muted. Then this, yeah, the products from the pyrolysis are, the main product is liquid oil, and then there is gas, which usually can be utilized in the pyrolysis to heat the process, and then char, maybe depending on the quality of the feedstock, char can be from 5 to 15 to 20%, depending if we feed a lot of, for example, glass fiber containing plastics, when we get a lot of char. But if we have not filled plastics, it can be very low also, the char content. And adsorbent are here mentioned because we studied also the utilization of adsorbent materials in the pyrolysis. We will have some results from those soon. So next slide. And the next we go to this experimental results, and these are the first pyrolysis experiments we did in about 200 liter scale, the reactor size, and there the two fractions studied was this one small household appliances based polymer, which was seen in the left side. It was quite mixed plastics, about 30% polyolefins, 18% polystyrene, 25% ABS, so very mixed. And then we had one fraction from large household appliances, which was very polyolefin rich, and especially polypropylene, but altogether there was about 90% polyolefins. And next slide. Tells about the first results, the columns there in the middle, so that the oil yield was around 70%. We had also as a reference neat polypropylene there, that also produced actually 75% of oil. That also produced char in that process, a little bit surprisingly high amount. But yeah, the pyrolysis as such was done in about 500 degrees non-oxidative atmosphere under nitrogen, and then the vapors from the reactor condensed into two-step condensation, and then actually they were combined to one liquid product. And next slide shows the boiling point distribution. Just to give an idea, but it's very wide boiling point distribution, the combined liquid product from a boiling point around between 50 and 600 degrees, but about 50% is in so-called naphtha region below 200 degrees boiling point, and then up to 90% is then either naphtha or middle distillates, not heavies. So usually it's so that the naphtha is the easiest to of course to then feed to the steam cracker. Next slide then shows some elemental analysis, and here the main idea is now to compare that what kind of elemental impurities we have: nitrogen, sulfur, chloride, bromide, oxygen, silicon, phosphorus. Those are typical there, in addition to carbon and hydrogen. And there is on the second column on the right, there is this kind of typical limits what is tolerated in the steam cracker feed. It was taken from one article. But anyway, those are about approximately the typical tolerated limits. You see that for sulfur the toleration is quite high, and that is because in the fossil oil also usually there is sulfur. And then you also see that our oil, okay, this is now the total oil, actually, so the coal boiling range. So if we would take only the naphtha, the results would be slightly different. But anyway, all except sulfur are all other elementary impurities are very high compared to the tolerated concentrations. For example, silicon, we only can have 0.5 ppm, while we have more than 500, 1000 ppm here. And then similar is of course for nitrogen, which is of course very high if there is ABS. So that was, in this case, there was about 2% nitrogen in the oil. So the what we can see from here is that this definitely needed a upgrading step between the liquefaction and the steam cracker. And the second example is the feed for the second set of experiments was from large household appliances. Okay, but this is not the same. And this time it's just very PE rich actually, and altogether also polyolefins are about 80%, and so it's quite suitable. Okay, there's 10% APS, but it's still like manageable. And the next slide is then showing the main results from that. We had targeted to study the effect of those adsorbents. 2 adsorbents were selected for the studies, calcium oxide, and then another adsorbent, which is that alumina-based chlorine removal catalyst, actually, a commercial one. And the third one, what we tested, was just simple water washing of the waste plastics feed. And these 2 pictures here on the left show chlorine, bromide, silicon, and sulfate contents. So this WLH is this washed feed, LHA non-washed without adsorbent, and then these 2 other columns are then with calcium oxide and this then alumina. And you can see that both calcium oxide and alumina caused a decrease in the chlorine, bromide, and silicon contents in the oil, quite significant decrease. Of course, not going to the close to the zero, and not close to the level which is acceptable for the steam cracker, but anyway, to the direction that then the next step would be then the upgrading, so meaning some kind of hydro treatment. So it's already better than those very high concentrations. Yeah, sulfate here maybe with this alumina, maybe it contain and leads some sulfur. We saw also that some trace metal contents where they increased also. So that was what I was going to present, and then somebody else continues from this.
Thank you very much. Yeah, from what we have seen and heard so far, we take the following conclusions. We see that the clustering approach for mechanical recycling can really lead to more sustainable recycling practices. We have improved material recovery rates. We have increased economic viability. For sure, we have more efforts in that sorting, but we see that the distribution of materials in the defined streams is much easier to handle with. Future research could focus on refining clustering algorithms and integrate real-time data analytics to adapt that to changing WEEE streams. For the high solvent-based recycling, we have seen that we have found quite nice recyclate qualities for polyprop, ABS, PC, ABS, and PC. However, we had sometimes the issue to pre-sort the WEEE fractions to come up to something like 70% feedstock purity. the upscaling to industrial scale has not been demonstrated so far. This is still pending, and here we are looking for collaboration partners. So chemical recycling, we can produce high quality pyrolysis oils from sorted WEEE plastic fractions. However, the mixing of different plastic types reduces the oil value, and therefore we have the need for extensive upgrading. Processing plastics separately is often more effective. Optimizing the pyrolysis conditions, such as using adsorbents, can increase oil products value. Lower contaminants reduce the need for upgrading, but that's for sure a separate upgrading step is always required before feeding that pyrolysis oils into a steam cracker. So in the end, just to give you an indication that these different technologies do not always have to compete with each other, they can even work hand in hand. And this has been exemplified in our INCREASE project for the large household appliances, plastics. And here we really made use of these sink fractions, where we used the solvent-based recycling to recover ABS, PCE, but also polyamides and polyprop, highly filled with glass fibers. We have a very large density fraction, which still needs some energy recovery incineration. And we have another roughly 45% in coming from the floating, and this can be by further NIR sorting separated into something which can directly be fed into a high valuable target, high valuable recompounding, as for example the polyprop, polyethylene, ABS, PS, non-halogenated fractions. And we have a drop fraction here, which is for sure also containing polyethylene, polyprop, and other dark plastics, which can undergo the so-called chemical recycling, pyrolysis plus upgrading plus steam cracker. Just to give you a bit of an example of how these fractions may look like, here from the total sink fraction in the beginning, then the separated sink fractions 1.0 to 1.1, and the larger than 1.1 density fraction. And you see here always a bit of a different composition of that materials here, with the majority being polyethylene, polyprop. Here, this is also containing some ABS, PS in addition. And here you see that even from the large one, we can make use of polyprop, polyamides, and where is it? The ABS, polycarbonate, whatever you look into. For the solvent-based, even from these shares, we were able to recover in 80% ABS and 18% of recycled ABS and 36% of recycled polyprop and polyethylene. And the outcome from this was for us still quite nice. So the ABS here is still in lab scale, not too good dry, a bit worse in drying, so still a bit too high. But for the polyprop, we are still sufficient that this is working quite well. And if you look into the leftovers in the solvent-based recycling so far, we see a large share of polyamide. So this is also suggesting that another dissolution step for polyamide may add another roughly 20%. So this is why for this approach we have very shortly the impression that this cascade allows to combine all the three technologies and to increase the overall yield. The experimental assessment so far showed us that we could make use of the sink and the floating fractions. The low density fractions were assessed in chemical recycling and could show a 70% yield of pyrolysis oils, which for sure require further upgrading and steam cracking. And for the high density fractions, as I said, 45% yield of ABS and PP, and probably another 21% from polyamide. So this is just to suggest how this could all work together, and probably a good time to start any questions.
Yes, although theoretically the time is over, so we also understand if you have to jump somewhere, but if you have questions, please ask them now and we'll make sure to answer them. And I will stop the recording so that you can also talk openly.